Recording in progress.
So we have another minute to go.
Maybe we could start.
Well, you tell us when to start.
I think it's time to start, as a proposal.
Okay. Okay, excellent. So I welcome you all to this session, which especially deals with the applications of quantum light. And our first speaker is Gerd Loek. The first paper is a large collaboration between Russian institutes and the German institutes. And Gerd is going to talk on applying squeezing by nonlinear amplitude dependent phase shape and what one can do with it. Gerd.
Yes, thank you, Girish. So first of all, thank you, Olga, for organizing the first and the number one seminar of this conference. And thanks for the invitation. So the topic I'm telling you about is also involves Luis Sanchez Soto from Madrid and Joel Corney from Australia, and my several colleagues from Nizhny Novgorod. So, why is it not proceeding? Wait a minute. Okay. So the experiments were partly done in the quantum confined intense laser lab in Nizhny Novgorod, and partly at Max Planck Institute for the Science of Light in Erlangen here in Germany. So the talk is about cell phase modulation optical fiber, which changes the quantum excitation of the mode function in the fiber, and then ultimately to apply this squeezing to interferometry, which has not been done before. At least Chi3 squeezing has not been applied so far, for reasons we'll discuss. So DC light effect, we know you apply light to a crystal and you change the phase. So the Kerr effect corresponds to a phase shift in phase space. If you have quantum uncertainty, then it is the coherent excitation which is shifted. But there's also an AC Kerr effect, which was first published by Gorgan Ashotovich Askarian in 1962. And then I think this was, I don't think they knew of each other's work. And then 64, 2 years later, by Chow, Garmeyer, and Towns. The formula I show here is from the Towns paper. So this is a nonlinear contribution to the refractive index, which gives you a nonlinear phase shift. A phase shift, nonlinear means the phase shift depends on the intensity, electric field squared. So what does it mean for quantum optics? And how does Kerr squeezing look like? We all know this amplitude dependent phase shift moves the higher amplitude a bit further than the lower amplitude. So the initially rotationally symmetric uncertainty in the coherent light field becomes distorted and squeezed. So if you take this formula and continue this, then for very high fields, you would expect such a spiral, but this is not correct. So we know that the quantum optical Kerr effect is cyclic. It eventually will go back to a coherent state because of the discreteness of the Fock states. With Mojde Najafabadi and Andrei Klimov and Luis Sanchez Soto, we looked at the regime up to which you can use this simple equation. And here you see on the top, this is this classical intensity-dependent phase shift model. and this is the proper, and the lower row is the proper quantum evolution. And the difference comes about when you see these quantum interferences in phase space. So these are phase space pictures. And what you see is that the difference comes about when the ellipse eventually starts to turn like a banana, and then basically you start to have interference fringes, namely like as if you would have like two coherent state, a cat state, you would get interference fringes here. So this is, I think, so you can guess how these interference fringes come about. So they become more and more narrow as you go further inside, and this is because the interfering parts are further apart in phase space. So in the fiber we are safe because the nonlinearity is such that we cannot go much anywhere close to this region where it actually starts curving. So we can use this simple model. So there is phase squeezing, there's amplitude squeezing, and there is this Kerr squeezing where the squeezed ellipse is under a skewed angle. Now in the experiment, early on, even before the first squeezing experiment, people understood, our colleagues on the theoretical side, they understood that when you do experiments and you look at some noise frequency and you look at this reduced phase amplitude squeezing at some particular noise frequency, that means that you look actually at two frequency sidebands, because there's an upper and a lower frequency sideband separated equally from the carrier, which both give contribution to the noise frequency omega. And it's the kind of interference joint action of the two that tell you whether you have squeezing or not. So if you have correlated noise in the upper and the lower sideband, which is indicated by the color code here, so the green is correlated to the green, the red is correlated to the red. So at one moment in time, you have green arrows, then you have brown arrows, then you have blue arrows, then you have red arrows. So what you see is that you have noise pointing in the amplitude direction. So there are lots of noise in the amplitude direction, but none in the phase direction. So this is phase squeezing. Now, if the symmetry axis of this correlation is tilted by 90 degrees, then, so the dotted line is the symmetry axis, then if you add them up, you get lots of noise in the phase direction, but none in the amplitude direction. So this is amplitude squeezing. And in the sideband picture, the Kerr squeezing means that you have a symmetry axis which is tilted by this Kerr squeezing angle. So in order to see this, you have to do the proper measurements. It's not as obvious as in amplitude squeezing. So the phase space picture tells you that the Quist uncertainty means that you have entangled sidebands. This is why initially the term two-mode squeezing was coined for these two correlated to entangled sidebands. Okay, so what has been done so far in Kerr squeezing? And I'm focusing on Kerr squeezing in optical fiber and nonlinear optical fibers. So this is the picture. I should probably get my laser pointer. Is this here? Yeah. So I think you can see this better. So this is the sideband picture. This is the single mode phase space picture. So in this sideband picture, basically, I have two single mode phase spaces at the two sidebands. So it's kind of an involved picture, but I think you understand. So the first people who did this was Bob Shelby, Mark Levinson, and colleagues. They used the reflection of an optical cavity. And why does this reveal the Kerr squeezing? Because by the reflection of the optical cavity, you can adjust things such that the carrier is phase shifted with respect to the two sidebands. And if this phase shift just compensate for the skewed angle, you go from Kerr squeezing to, in this case, this is large phase squeezing. So this is large phase noise. So this is amplitude squeezing. Right. So red and red. All these arrows add up to give you some noise perpendicular to this shifted, rotated carrier. Then you can use a symmetric Sagnac interferometer. You can use spectrofiltering. You can use asymmetric Sagnac filtering, which was initially proposed by Kitagawa and Yamamoto, and this is in a nonlinear interferometer. You can have the nonlinear part in one part of the interferometer where there's lots of intensity, and a smaller component which does not undergo nonlinear interaction at the output of the Sagnac interferometer will then interfere. And if this shifts the ellipse such that in the new position, the initially squeezed ellipse is now at right angles with respect to the amplitude, then you have amplitude squeezing. But all this, I mean, this uses interferometers to make the squeezing visible, but it does not improve the phase sensitivity of an interferometer. The squeezing in fibers, which gave probably the best squeezing, is from our lab 2008. And also this has not shown interferometric sensitivity enhancement, but the new experiments are based on this. So I'll show the picture here. Actually, this is the same Joel Gorney, who is now also author on this paper. Here's the fiber. This is where the squeezing starts. It's a polarization preserving fiber with two axes, fast and slow axis. Now we take an initial pulse, split it in two, delay one, and they are orthogonally polarized. We first launch a pulse along the axis, the slow axis. Then later we launch a pulse polarized along the fast axis. And the separation is such that at the output they coincide in time, as shown here. And then you can do a Stokes measurement, and the Stokes measurement mixes these two polarizations basically. And if you adjust the phases such that here it is sigma plus polarized, you adjust the Stokes measurement, you have to measure the linear polarized S1, S2 Stokes parameters, and then you can map the squeezing. And that gave, I think, oops, I thought I gave the number. Here, up here it is. It gave the experimentally observed value was almost 7 dB squeezing, 6.8 with this error bar. So this is an interferometer because you have the pulse here. It's split on this birefringence compensator, and then it's joined in this Stokes measurement that basically mixes the two modes again, but it does not give intensity enhancement. So now we understand that already in 2008, had we put like a glass plate in here, induced some birefringence, we could have seen this kind of phase polarization-dependent phase shift with below shot noise sensitivity here. But at that time, we did not understand properly. But there were other groups working on the same topic. They also didn't understand. So we are in good company. But in hindsight, I was thinking we could have done this experiment easily at the time. So first of all, now we have an improved setup. This was a suggestion by Alex Andrianov and Nikolai Galinin from the institute in Nizhny Novgorod. They said instead of having this birefringence compensator, this is too complex. We can do it much more simple. More simple means also more robust. And this is cut the fiber in half in the middle, rotate by 90 degrees and splices together. We can do this with low losses. And then the light, which will walk along the slow axis first, will then in the second half walk along the fast axis and vice versa. So what coincides in the beginning will coincide at the end. And then you can do the Stokes measurement and map the squeezing, and everything is the same. So we have seen slightly more than 5 dB squeezings here, which is slightly less what we have seen a while ago, but we have not optimized the fiber lengths yet. These are the pulse numbers. So this is this kind of slightly more than 5 dB squeezing. This is dBm here, the vertical axis, and it's very stable. this shows 100 seconds. We can also switch it off, come back in the next morning. It's very nice. So this is a very nice squeezing source. But still, this is not squeezed interferometer where the sensitivity is enhanced beyond the shot noise. So if in a normal interferometer, you have your coherent input, and then there's some squeeze light entering on the other side. And then the question is, what do you have at the output? So you have two modes. The vector properties of light have two modes, means two amplitudes and two phases. So two complex numbers, and these relate to the Stokes variables or the equivalent Stokes. So these are not necessarily now polarizations. In general, these are just two modes. So there's an equivalent formulation. So the generalized Stokes variables for two modes, but just the same. So then one of the Stokes variables will give you the population difference between the two modes. And in the equatorial plane, you will have superpositions, symmetric superpositions between the upper and the lower mode. Now, if you have an interferometer where you have Kerr squeezing in the two arms, like you have in a fiber, so if these are, for example, horizontal and vertically polarized modes in a polarization preserving fiber, then you launch light, which, for example, if you have a fiber which is under 45 degrees with respect to the axis, then it will split up into the two modes. It will exit simultaneously if you have this this cut, as I described. And so then you will have squeezing. Now, if you look at this interferometer in the this Poincaré picture, so this is like a joint view of the situation, then you will see that as a function of path length difference in these two arms, the state will propagate on a trajectory which is a great circle in this two-mode phase space on this Poincaré sphere. And the squeeze ellipse will be tilted actually under fairly steep angles. So if you look at the noise, you have to project onto the trajectory, and this is even worse than a coherent state. So this doesn't help. Now, the new thing is, if you do a basis change, then let's say you have initially you have horizontal and vertical, and then these two bases you rotate by a small angle theta. So horizontal is not really horizontal, but slightly tilted, and vertical is perpendicular to this slightly tilted horizontal. And if you do it right, basically like this squeezing corresponding to the squeezing angle, then in this second part, now you will be sensitive to this, to phase differences better than the shot noise. And basically what it means, this basis change means that you leave the squeeze ellipse unchanged, but you rotate the trajectory, and you have to rotate it such that the trajectory is perpendicular to the long axis of the squeezing ellipse, of course. So this is the solution. It's as simple as this, and I'm a bit embarrassed we could have done this earlier. So this is the quantum enhanced phase sensitivity. So first I find out that, I think it was at Marlon Scully's conference this January, I found out that in cold atom interferometers, people have started to do this trick since 2010. There you have Gross-Petajewski equation. Mathematically, it's the same. You have an equivalent of a Kerr squeezing ellipse under some odd angle. Then I thought, oh my God, 2010, this is, we could have done this 2 years earlier when we were thinking about this. We missed out. And then Nikolai found this paper by Shirazaki, a single author paper from '91. Shirazaki, he was collaborating with Hermann Haus a lot at MIT, otherwise working at a Japanese company. And he already in '91 basically proposed this. But this paper was cited 6 times. Now we cited it. It's the 7th citation, and 4 citations by Shirazaki himself. And so basically it was not noticed in the community. So now we try to advertise this. maybe the way it was written, we didn't understand, other people didn't understand, but basically he should get the credit. The cold atom people, they quote someone else, also Japanese people from 93, I think. So I told them, Shirazaki, you should cite Shirazaki. Anyway, so if you have a top view, this is again the trajectory in this skewed ellipse. So the trick is either to rotate the trajectory, or alternative, you could keep the trajectory the same and rotate the ellipse, so both as possible. We know how to do it. In the case that we do it, it's by this rotating, doing this basis change. So again, I cannot highlight this often enough. Shirazaki should have been cited much more. So this is quite nice because it gives a fairly straightforward way to use Chi3 squeezing in interferometry. So here is a sketch, a general sketch. This is the interferometer. We have it in a fiber, but this is written as a normal interferometer with a Chi3 carrier effect in both arms. You have this carrier tilt. Here you induce the basis change with the half wave plate. And then here is the interferometer where you induce some phase change. And then you do this Stokes parameter measurement. And the way we do it, this interferometer in our case is simply a glass plate just for the demonstration, which we squeeze mechanically. So we induce birefringence. And this induces a differential phase shift between the two polarizations in this tilted basis. And this we can measure very sensitively. And we don't see quite the 5 dB of squeezing that we have if we only look at the squeezing, but we see a 4 dB improvement of the signal to noise ratio. And we are quite pleased with this. So if you look at the at all the papers, starting with Jeff Kimball and Dick Slusher's group in the 87, who have applied squeezing to enhance the sensitivity of an interferometer. All of them so far use parametric down conversion, Chi2, and ours now, so the publication came out in January, and ours is based on Chi3. And these 4 dB don't look so bad if you look at the numbers that Chi2 squeezing interferometers had until 2-3 years ago. Since then, they went up to 10.5 dB squeezing, but ours has only started. And we think it's still, we have to develop this and see how far we can go. We have to optimize parameters, and so we think this can be compatible, and maybe there are some, there's room for this Chi3 squeezing enhanced interferometer. So with this, at the end, I hope I didn't go over time. Thank you very much for listening.
Well, thanks, Gerd. So we have time for one quick question. Well, if not, okay.
Question.
Yeah, Vitali.
For this system, do you need a strong signal to implement kernel linearity, or it's enough signal on the level of a few photons, and this system can be used as a source for the squeezed single photons or so system?
No. So what? Yeah, I didn't tell you. So what we, in order for this nice squeezing, it's better to be in the soliton regime, so that the nonlinearity in the fiber is so. If you have a soliton, the pulse stays together, and because of the higher amplitude, you have this higher nonlinearity throughout the fiber. If the pulse would disperse, if it's not a soliton, the effect would be smaller. Yeah. So, but it's not so strong. It's, I think, wait a minute, I think the soliton, the pulse energy is something like 100 picojoule, but still it's like 1 million photons in the pulse.
Okay,
it's not 10 to the 20, it's only 10 to the 6 photons, but it's not, it doesn't work at the single photon level. But It works for interferometry. So and in very sensitive interferometry, like in gravitational wave detection, you have much more average power than we have even. And so in principle, in some cases, when you look at very high sensitive interferometry, the high power is not so bad, but it does not give you squeezing at the single photon level.
Okay, thank you, it's clear.
Okay, thanks, Gert. Let's move on to the next speaker.
Thank you.
So our next speaker is Alexei Kalachev from Kazan Scientific Center, and he will be talking on quantum hashing by a single photons.
Thank you, Girish, and just let me. Yeah, I think it's good. And of course, I would like to thank Olga for inviting me and for giving me the opportunity to present our recent experimental and theoretical results devoted to developing quantum hashing concept using single photons. This work has been done in collaboration between experimental group from Kazan Scientific Center of Russian Academy of Science and theoretical group from Kazan Federal University. So this is outline of my talk, and I'm start by general remarks about cryptographic hash function and quantum hashing concept. In general, the main task of hashing is to reliably present information, for example, strings or long strings over some finite alphabet, in a compressed form, which is called hash, that allows us to distinguish the initial long strings effectively. And such a mapping is known as a hash function, and it's widely used in various data storage and retrieval applications to reduce the data access time. In addition, hashing is widely used in many parts of modern cryptography, such as verification of message integrity, fingerprinting, digital signatures, etc. For cryptographic applications, hash function should satisfy two main properties: one-way property and collision resistance. The first means that to find the hash value for an arbitrary input string should be a simple problem, but to restore an input string from its hash should be a computationally hard problem. And the second property means that the situation when two different inputs have the same hash, such situation is called a collision, is infeasible. In other words, to find a collision for cryptographic hash functions should also be a computationally hard problem. And the promising generalization of the cryptographic hashing concept in the quantum domain, namely quantum hashing, has been suggested in papers by Farid Ablaev and his colleagues. In this case, the hash function is defined as a mapping of classical input strings into quantum states. And such mapping should satisfy, again, two main properties. First, so long strings should be mapped to quantum state of a small dimension or state composed of a small number of qubits. And second, for two arbitrary different inputs, x1 and x2, the fidelity between their quantum hashes should be small. So the first property provides a good one-way function due to the fundamental Holyver theorem. So we cannot extract more information from quantum state than the number of qubits. And the second property, again, provides good collision resistance. So probability to find a collision is bounded by the value of fidelity. And such functions can be used as basic ingredient for various quantum cryptography protocols, such as privacy amplification and quantum key distribution, quantum fingerprinting, quantum signatures, etc. However, the proposed constructions of quantum hashing in these papers are maximally efficient if completely entangled states are involved. So it's difficult, it's hard to prepare such states. And recently, we have suggested to construct a quantum hash via a sequence of single photon states, qubits or qubits, which does not require complicated entangled state and simplify implementation. And the main idea of quantum hashing here is that the state of each qubit or qubit is determined in a specific way by the whole input X. And the advantage of such an approach is that destruction of some of the qubits has no negative effect on the information about the input state. So let me discuss our approach in more detail. For the quantum hash to be implemented, we can take advantage of conditional preparation of single photon states via spontaneous parametric down conversion. And due to phase matching, there are several conservation laws, such as frequency conservation and orbital angular momentum conservation. The latter is observed in case of collinear SPDC when all the interacting fields propagate in the same direction. And this feature allows us to generate high-dimensional single-photon qubits and two-photon entangled states in the orbital angular momentum basis. So detecting one photon, one of the emitted photons, for example, signal 1, indicates the presence of a second one in another channel, so that we obtain heralded single photon source. And due to the conservation law for orbital angular momentum, the spatial state of heralded photons reproduces that of the PAM field if another photon is detected with a specific value of orbital angular momentum, for example, with 0 value. And in doing so, we can prepare single photons in a superposition of different orbital angular momentum states by manipulating the PAM field alone, which provides maximum heralding efficiency because heralded photons need no additional spatial transformation. And to construct the multi-qubit hash function, we use single photon qubits as superposition of Laguerre-Gaussian modes with a 0 radial index. So this is a sketch of our experimental setup. It consists basically of two parts. One part provides generation of single photon states. So using special light modulator, we prepare a superposition of Laguerre-Gaussian modes in the PAM field before it enters the nonlinear crystal. And heralding photons are sent to another special light modulator and collimated into single mode fiber, which filters the states with 0 orbital angular momentum here. And finally, by getting heralded signal, we prepare the second photon in the same superposition of Laguerre-Gaussian modes as for the PAM field. And the second part of the experimental setup is used for measuring spatial states of the emitted photons using well-known phase flattering technique. So here's another part of spatial light modulator is used for spatial transformation from the state that we want to project on to the Gaussian mode, so that successful photon detection after propagation through the single mode fiber means successful projection measurement. So let me discuss now some details of our quantum hash function. So the classical input X is encoded by the equally weighted superpositions of single photon states with different values of orbital angular momentum. And the properties of this function is completely determined by the set of parameters S, which define relative phases for each qubit in a specific way. In particular, in order to minimize the error collision probability, the parameter set of this parameters S is chosen in such a way that the pairs of hashes for different inputs give the minimum fidelity. And the search for this set may be done with some heuristic algorithm like genetic algorithm, or even with an exhaustive search for small values of qubits. And to measure the collision probability in experiment, we consider we compare different quantum hashes in the worst case scenario, when quantum hashes with different arguments have the maximum fidelity for a given set of parameters S. And in our experiments, we demonstrate the basic properties of quantum hashing for the case of classical input consisted of several bits, and quantum hash consisted of several single photon qubits of qubit. And the number of bits and qubits is limited by the accuracy of the relative phase control. In particular, we prepare single photon qubits as an equally weighted superposition of two Laguerre-Gaussian modes with opposite values of topological charge of orbital angular momentum in order to cancel contributions of the GUI phase. And in this case, the accuracy of relative phase control was about pi over 256. And regarding high dimensional states, we prepare single photon Q-terets and Q-quarks, as shown in this slide, as superposition of different values of angular. And this slide illustrates comparing experimental and theoretical collision probability, decoding probability for the worst case scenario and for different values of orbital angular momentum. The main conclusion from this result is that we have good agreement between theoretical and experimental values, which does not depend on the topological charge value. Therefore, it is possible to use multiplexing different orbital angular momentum states, which can make quantum hash function preparing and measuring faster. In this case, we can see the input state consisted of 9 bits, and the output hash function consisted of from 2 to 8 qubits. And this slide shows again comparison of experimental and theoretical error rates, collision and decoding probability for the worst case scenario, depending on different dimension of quantum states. And you see that the number of information carriers decreases with increase of their dimension for an optimal ratio between collision and decoding probability. For example, if we limit both probabilities by 20%, the optimal number of qubits that needed to compress 8-bit classical information proves to be 5 for qubits, 3 for Q-terets, and only 2 for Q-quarks. And moreover, for a given dimension of total quantum states, in our case 16, using smaller number of higher dimensional qubits gives smaller collision probability, which is another benefit from using high dimensional carriers, high dimensional qubits. And finally, let me discuss the total scheme of quantum hash verification that can be implemented for a single quantum hash state, for a single hash. We start by receiving a quantum hash of some generally unknown value x1 as a sequence of m single photon states in overall factorable state psi of x1. Then we check whether x1 equals to some predefined x2 or not via a single photon projection measurement. And if all measurements confirm that the measured state is the same as expected, then the final result of the experiment is x1 is equal to x2. Otherwise, we have to conclude that they are not equal to each other. And to perform projective measurements, we have to prepare a complex phase mask on a special light modulator, which is appropriate superposition of detection mask for expected state psi j x2 and for d-1 additional orthogonal state. If x1 is equal to x2, in the first channel, the detector of the output psi g of x2 would always click, while the other detectors would never click. If x1 is not equal to x2, each of the detectors might click, but the probability of error statement that x1 is equal to x2 is bounded by the contraction of our quantum hash function. And finally, if none of the detectors had clicked, then the qubit should be considered as lost, and we either request its resending or tolerate the higher error probability. Okay, now let me come to the conclusion. So in this in our recent works, we develop quantum hash concept, which is constructed as a sequence of single photon qubits. And we perform a proof of principle experiment demonstrating this construction using orbital angular momentum encoding. And we show that collision probability does not depend on the topological charge value, which opens the possibility to use multiplexing of different orbital angular momentum bases. And finally, we show that the number of information carriers decreases with increase of their quantum state dimension, which potentially means that it is better to use high dimensional states for implementation of quantum hash protocols. Thank you for your attention.
Thanks, Alexei. So we have time for some questions. Yes, Gerd.
Yeah, thank you, Alexei. This is very nice. So in the slide before the conclusion, this projective measurement, are all these psi j of the, are they all orthogonal? No, it probably depends on whether x1 and x2 are orthogonal. I was wondering in how far this relates to a sorter, but a sorter I think sorts into orthogonal states.
Yes, it may be considered as a sorter because we separate among orthogonal states by using these masks. So first of all, we should project to the state psi j x2, and we should construct a set of orthogonal states relative to this one.
Oh, it's like a sorter, yeah. Okay.
Yeah.
Okay. Right. Yeah. Thank you. Very nice.
Yeah, Vitali.
I have just general question. Is it possible to use this hashing protocol and hashing system to demonstrate some features of the quantum supremacy? Because you mentioned that this hashing is related to the number p hat for computing processes. So like a sampling, boson sampling. Is it possible to use this system in the similar way?
I think the main advantage of quantum hash function with respect to classical hash function is that we have, due to Holevo theorem, we have like intrinsic one-way property based on laws of quantum mechanics. So this is I think the basic difference between quantum hash and classical hash. In both cases, I think the optimal number of quantum states scales logarithmically on the number of input of the size of input state. But in this context, I think supremacy is not relevant characteristic. But with respect to calculation reversal function, I think this is the point.
Okay, so Maria, you can go ahead with your question. Are you muted, Maria?
Microphone. Or not? Okay.
No, we don't hear you, Maria.
Now?
Yeah, yeah.
Yes.
Sorry, it was just the wrong setting. Thank you for the talk, Alexei. Just a very technical question. What is the heralding efficiency when you prepare these photons?
Well, it's not high. I think from 10 to 20%.
Okay. Thank you.
Yeah, let's thank Alexei again and move on to the next speaker. So the next talk would be given by Luis Davidovich, and he will be talking on quantum metrology of Pauli channels.
Oh, hello. Thank you, Girish. And of course, I want to thank Olga for the organization of laser physics, now a traditional conference in many fields actually related to laser physics. And thank you also, Olga, for inviting me to give this talk in this session. So I'm going to tell you about some recent work. It's actually submitted for publication on quantum enhanced metrology of Pauli channels. Let me first introduce the theme. Of course, quantum metrology is related to quantum sensors. And quantum sensors I believe, it's one of the important pillars of quantum information nowadays. You can, for instance, use a single atom to map the structure of a biomolecule. You can use magnetic sensors for brain imaging. Gravimeters are available. They are based on atom interferometry, and they can be used in principle for surveying underground water and oil. Quantum gyrometers and accelerometers may allow GPS-free navigation. Atomic clocks have reached a fantastic precision with a systematic uncertainty below 10 to the minus 18. And of course, we all know about LIGO, which now is using squeezed states of light in order to enhance the detection of fantastic events in our universe. Now, all of that is related to parameter estimation. And the general idea of parameter estimation is the following. You have some dynamical process that depends on some parameter. You send a probe to the process. You prepare the probe in some initial state, and then you measure the final state of the probe, which is chosen, the whole thing is chosen so that the final state depends on the parameter you want to estimate. And by measuring the final state, you get an estimator of the value of the parameter. So that's the general idea. Of course, it requires choosing a suitable initial state and a suitable measurement, and also requires the association to each experimental result a value of the parameter. Now, this is true for classical metrology and for quantum metrology. In general, quite generally also, in both cases, you have a bound for the precision estimation. This precision is defined in terms of unbiased measurements by the variance. It's just the variance between the measured values of the parameter and the average value of all the measurements. So that's the uncertainty, if you want, of the estimation. And the Kermer-Round bound tells us that this uncertainty is bounded below by this equation here, where in the denominator you have the number of repetitions of the experiment and a function of the parameter, which is the Fisher information. And this Fisher information can be written in several ways. Here, I just write it like that, which I find a very nice way of writing it for reasons which will become evident immediately. So here, pk of x is the probability of getting an experimental result k if the value of the parameter is x. And you see that you have here a derivative of the square root of the probability. We can show that this inequality here is saturated for Gaussian states, or if the number of repetitions of the experiment that was shown by Fisher, and that's why this is called Fisher information. This is a derivative of the square root of the probability, and therefore it is the speed of change of the square root of the probability. And you see that the faster the speed of change as the parameter changes, the better will be the precision in the estimation, because f of x comes here in the denominator. So the Fisher information gives us an information on the speed of change of the probabilities when you change the parameter. In fact, you see that the precision increases with the distinguishability between pk of x and pk of x plus delta x. So you change the parameter a little bit, and you have another distribution of probabilities. And if they are very different, that of course increases the precision in the estimation of this parameter, of the parameter. Now, you can generalize this expression for continuous measurements, and you can just write this instead of a sum as an integration. Now, this is just classical estimation. How can we get a quantum Fisher information? Well, we start with the same definition for the Fisher information as you had classically. So again, you have here a derivative of the square root of the probabilities, or the probability density. Psi here is an experimental value. We integrate this over all possible experimental values. Now, the probability here is now given by the quantum mechanical expression. It's just the average of this operator here, which is in general POVM. Of course, a particular case of that, a special case, is a case in which E is a von Neumann projector, but you can do something more general with operators that are not orthogonal, but still they have this completeness relation, and that defines a POVM. So it's a set of positive semi-definite Hermitian matrices on a Hilbert space that sum to the identity matrix. We must do that so that the integration of the probability gives B1, but they are not necessarily orthogonal. So you see, this corresponds to a given quantum measurement. It corresponds to a given choice of this POVM. The ultimate lower bound for the estimation is given by optimizing the Fisher information over all possible choices of quantum measurements. And this defines the quantum Fisher information. So that's the measurement is defined in terms of the measurement, which gives me the best bound for the precision, the best lower bound for the precision. Again, as in the classical case, the quantum Fisher information measures the distinguishability of the parameter-dependent probe states psi x and psi x plus delta x. And in fact, it gives us the speed of change of the distance between these two states as x changes. And this is an exact relation, and that delta x is very small for small changes of the parameters, so it's the limit of this expression. It's just the scalar product between psi x and psi x plus delta x. The magnitude of that, as when delta x is very small, goes to this expression here. And you see that the quantum Fisher information shows up here. So indeed, square root of this expression here can be considered as the speed of change of the state of the system as x, the parameter x changes. Now, a good question is how to get the quantum Fisher information. After all, maximizing the Fisher information over all possible measurements does not seem to be an easy task. There is, however, a general expression for the quantum Fisher information, which is given here. So it's a trace of the final density operator of the probe, which is dependent on the value of the parameter, multiplied by another operator the operator L to the square. And this operator is called the symmetric logarithmic derivative. And it is defined implicitly by this expression here. So it's the derivative of rho with respect to x is given by an expression which defines L. And from this expression here, if you take the matrix elements in the basis of eigenstates of the density operator on both sides, you can show very easily that you can find the matrix elements of the symmetric logarithmic derivative, and they are given by this expression. So if you know the matrix elements of the density operator, and if you can diagonalize it because these are eigenstates of rho, then you can solve for this operator. Of course, diagonalizing the density operator for a system in the Hilbert space with infinite dimensions, it's a challenging task, but sometimes this can be done. If you have a pure state and a unitary evolution of the probe, then the quantum Fisher information has an explicit expression in terms of this operator h of x, which is defined by this derivative of the evolution operator. Okay? So if you have an evolution operator which is x-dependent, this describes the evolution of the probe, then you can find this operator h here, and from that you can calculate the quantum Fisher information as this variance here associated to this operator. So for pure states, we can calculate the quantum Fisher information. Now, if you have a noisy evolution of the probe, then in general, L is difficult to evaluate. Analytic expressions can be obtained for Gaussian states or low-dimensional Hilbert spaces. And what I'm going to show you now is an example of calculation of the quantum Fisher information. It's an example in a low-dimensional Hilbert space, which brings us, however, interesting properties in a problem which is of quite general application. So I'm going to discuss here the quantum metrology of Pauli channels. Pauli channels are defined by this expression here in blue. You operate on a density operator. That's sometimes called a super operator or a channel. And this is the density operator of the probe. And what this equation describes is that there is some probability that the channel does not affect the probe, which is 1 minus theta. And there is some probability, theta, that the channel does change the probe, does affect the probe. Here we have the 3 Pauli matrices applied on the density operator of the probe with some coefficients in front. Now, these operators, these coefficients here have a physical interpretation. Theta is the probability of having an error on the density operator of the probe. And if you multiply theta by Q alpha, that's the probability of having a specific error associated to one of the Pauli matrices. Of course, since the total probability must be equal to 1, you must have this expression here, sum of Q alpha equal to 1, and Q of alpha is larger than 0. So you can treat them as probabilities. So you have here 3 possible errors because you have 3 Pauli matrices. And this is very much described in detail in the book by Nielsen and Schwang. The Pauli matrices sigma x corresponds to a bit flip. In graphical terms, if you start with a spin represented in the Bloch sphere shown here, the bit flip will transform this sphere into this solid here. The idea is that sigma x does not change anything in the x direction, but it does change things in the z and the y direction. If you have a phase flip, then you have a compression in the x and y direction, but nothing changes in the z direction. And finally, if you have a sigma y Pauli matrix operating, this is a bit phase flip. So from the initial Bloch sphere, unitary Bloch sphere, you get then this distribution here. So I'm dealing now with spins, but of course you can consider this as photonic polarizations. So it's a quite general treatment for qubits that have to go through a channel. and this channel is a noisy channel. So this you start with a unit sphere and you end up with a compressed sphere. Now, in this talk, I'm going to consider a special case in which I have all the probabilities of all the errors equal to each other. So that means that you have here an isotropic depolarizing channel, which can be written in this way here. So now I have set all these Q alphas here as 1/3, and this is an isotropic channel. So what this does to an initial Bloch sphere is just to compress it in all directions. So you have here a sphere of smaller radius, and that's the effect of the noisy channel. You start with a pure state, and you end up with a mixture. Now, our aim here is to estimate the probability theta of having an error. And this was detailed in the paper with Ruiné Matos Filho, which is submitted for publication. And in this paper, we actually consider other cases, not just isotropic depolarizing channels, but also anisotropic channels. But here, I'm just going to deal with the isotropic channel, which has some funny properties, as I'm going to show you now. So what you want to do is the following. We have here the depolarization channel on the left. You have some qubit coming, and you want to calculate the quantum Fisher information for this process. Remember, this quantum Fisher information will give me the ability of, or measure my ability of estimating the probability of depolarization. Now, this is easy to calculate. It's a two-dimensional system. And we find that the quantum Fisher information for just a single probe, this P here means probe, is given by this expression. Now, you could try something more sophisticated. You start with an entangled state of 2 qubits, and you send 1 qubit through the depolarization channel as before, but then there is another qubit which does not go through the depolarization channel, but it's initially entangled with this one. And then you measure the final state. Now, the quantum Fisher information for this case, when you have a probe plus an oscilla, is given by this expression here. One can show that this quantum Fisher information is always larger than this one. So that means that if you want to have a better precision, it's always better to send an entangled state like this one. You see that if your sample is fragile, you are still sending just 1 qubit through the sample as here, but you have this auxiliary qubit here, which increases the quantum Fisher information and therefore increases the precision of the estimation. Now, the trick here is to start with an initial state, which is a maximally entangled state, and to do the measurement also in the Bell basis. So you project the initial state onto its orthogonal state in the initial state. So it's a binary measurement in this case, and we can show that by doing that, you get this quantum Fisher information. We have also shown that separable states always lead to the quantum Fisher information for single probes. Of course, if you just have a probe state, that's trivial because this one does not undergo any depolarization. So the quantum Fisher information will reduce to the one for the single probe. But even if we have a classical correlation, we still get the quantum Fisher information for single probes. So initial entanglement is essential in this case to have quantum advantage. And the entanglement measurement, we have also shown that it's essential for getting quantum advantage. If you just measure a classical and have a classical measurement, even with classical correlations, this does not help. Now, it's interesting to remark that if you have a maximally entangled state to start with, the reduced density matrix for both qubits is just proportional to the identity. That's true for the initial state and also for the final state. So there is no information on theta if you measure each qubit. The information on theta is in the entanglement. And that's interesting to keep in mind. And these are our final results. We compare here 3 different quantum Fisher informations. And in orange here is the quantum efficient information for two entangled probes going through the channel. So both of them go through the channel. In blue, you have the result with an oscilla, like I have shown here. And in green, you have two photons through the channel. In order to have the same number of photons all the time, so the same resources in the beginning, we consider that now we send two photons to the channel, they are not entangled, and we have to compare these three situations. And you see that the result is really quite interesting because it shows the power of entanglement. Theta, remember, is the probability of having the channel acting on the system, of changing the state of the probe. Theta equal to 1 means that you have complete depolarization. Theta equal to 0 means that the channel does not act. And what you see here is that if you have strong depolarization, the probe plus oscilla is much superior to any of the two options, to the product state or the two entangled states going through the sample. So this shows that there can be a big advantage, especially if you have strong depolarization, in using the oscilla strategy. Now, it's interesting also to remark that if theta is larger than 1/2, so it's just a central point here, the probe plus oscilla becomes better than the product state. You see here from the plot, but also one can show that the output becomes completely disentangled. So quantum advantage here comes with complete disentangling. So the final state is not entangled anymore. And in this sense, this, for those who know it, this looks similar to quantum illumination. Something similar happens there when you try to see an object in a noisy atmosphere. Again, quantum advantage comes together with complete depolarization of the final output states. Finally, I want to show you people with whom we have interacted and which have helped us to understand better this field of quantum metrology. At the Federal University of Rio de Janeiro, you have here the students that have participated in this in the AVOR. Some of them are professors now, and these are the professors that have helped to in this project. Nissim, Ruiné, and Fabricio are theoretical physicists. Gabriel and Gabriela are experimentalists, and we have also collaborated with the group of Serge Haroche at Collège de France, and with Girish Agarwal at Texas A&M, with whom we are still collaborating with many ideas, and I'm very thankful to Girish for this. So that's it. Thank you very much for your attention.
Thanks, Luis. Well, we have time for one quick question. Well, Masha. Suhail, sorry, Suhail.
I didn't raise my hand, but thank you very much for the talk.
Thank you, Maria.
Okay, Suhail, you had a question?
I just wanted to know, I mean, the state that you chose, the entangled state that you chose was 0, 0 plus 1, 1. What would happen if it was 0, 1 plus 1, 0?
Very good. So any maximally entangled state will do
Would
it.
do.
Yes, anyone. Okay?
I mean, the reason why I asked this question is because of the resources.
Mm-hmm.
I mean, when you have an entangled state, then you have apparently more resources, and whether the improvement sort of corresponds to the resources that you have.
Right. But you see, you are frozen now.
Hmm?
Can you hear me? Yes. Okay. No,
yes,
your image froze a little bit. So yeah, but you see, in both cases, 0, 0 plus 1, 1 or 0, 1 plus 1, 0, we have two spins, or if you want, two photons coming into the system, probing the system. One of them is oscilla, the other probes the system. So the resources in terms of number of spins or number of photons used is the same. Okay, is the same. Of course, from the point of view of the sample, having just one photon going through it, it's great, right? Because, especially if it is a fragile sample. But we don't. We really want to consider the worst situation, because then our method will still be better. Will be much better. Okay, even if you have one photon going through the sample, you have this oscilla that does not go to the sample, and you get a big advantage. But just to make it as hard as possible, we compare this with 2 photons going through the sample to keep the resources the same, the number of resources the same.
Okay, let's thank Luis and move on to the next speaker.
Thank you.
So, who is Suhail Juveri from Texas A&M University. And he's going to talk on waveguide cavity with atomic mirrors and applications.
Okay, so thank you very much, Girish, and of course, I'm also very grateful to Olga for organizing this symposium and to give a talk here. What I would like. Can you hear me?
Yes.
Yes.
Okay. Okay, so what I would like to talk about is some work that we have done recently on the waveguide cavity with atomic mirrors, and then I'll discuss, if depending upon how much time I have, on the applications. So this is the outline of my talk. I'll first describe the motivations for studying this problem of photon transport through waveguides. I'll very, very briefly discuss, without really any mathematics showing, the static and the dynamical solutions. And then I'll talk about some applications that we have been studying, like atomic mirrors, single photon frequency comb, deterministic quantum state preparation, and inversion via squeezed vacuum. Okay, so basically, many of us old enough in 80s and 90s were working on this kind of setup where there were these cavities and the atomic interaction with it. So the cavity QED was really the order of the day. Now what we are talking about is waveguide cavity QED. And here we are basically considering the interaction between some emitters of light and which are confined in a single waveguide. Motivation comes from many directions. Photons are, of course, ideal carriers for quantum information. So it's very interesting to study their behavior in a waveguide. And then manipulating and routing photons could have applications in quantum information. And then 1D waveguide, this can enhance the photon emitter coupling, but also guide photons. So we can study these effects there. And perhaps the main reason why we got involved in this problem had to do with the fact that it is possible to create a squeeze vacuum for all modes. In 80s and 90s, when squeezing came along, people were always talking about what if we have a squeeze vacuum interacting with an atom. Many novel effects were predicted. But of course, creating squeezed vacuum states for all modes in a 3-dimensional case is not so easy. Here in 1 dimension, it becomes possible, and we have some interesting results about that. Okay, so the problem basically, so I'll start with the simplest and go on. So the simplest problem that we can consider is a wave packet, a single photon wave packet incident on an atomic array, in this case, just a single atom, and part of the amplitude will be reflected, part of it will be transmitted, and we can study both the spatial and the spectral distribution of the wave packet. And there are many methods to deal with this kind of a problem. In 2016, we wrote a review article where we tried to present some of these approaches to the problem, theoretical approaches to the problem. Okay, so I mean, without giving any details, I think one of the very earliest result, which was obtained in this paper, which is now a classic. I mean, this was really the field opening paper, in the sense that the mathematical tools that were defined here really help us in solving many more complicated problems. And it turns out that if I have a single photon incident on a single two-level atom, then we have reflectivity, which is given by this expression. Here, gamma corresponds to essentially the coupling strength. So this is a decay rate due to the coupling between the quantum emitter and the waveguide modes, whereas this small gamma, this is the decay rate due to the coupling with the modes outside the waveguide. And the interesting thing is that in the case when gamma is equal to 0, when we can neglect these modes, which corresponds to decay in the non-propagating modes, then it turns out that at the resonant frequency, we have a perfect reflection and zero transmission. I mean, for a detuned case, of course, there is some loss as far as reflection is concerned. Now, this is something which gives us an idea that perhaps we can use these atoms as mirrors. So for a single atom, this is sort of the description. So here we are talking about a single photon pulse going to the two-level emitter system. Part of it is reflected, part of it is transmitted. We define our state of the photon, state of the system to be like this. This is excited state and no photon, and photon emitted here. And in order to calculate, for example, the spectra, we just, I mean, instead of doing a rigorous calculation through two-time type correlation, we just calculate these amplitudes, the right-going amplitudes and the left-going amplitudes, and the modulus square of these amplitudes would correspond to the spectrum. And here what we see is that this is the incoming wave, this is the reflected part, and this is the transmitted part. And what we see is that in the transmitted part, there is some kind of a signature of interference. And this happens because the reflected part consists of just the reflected part, but the transmitted part consists of the transmitted part plus the incident wave, and that can give rise to such interference behavior. As far as the spectrum is concerned, so here this dark black line corresponds to the incoming wave, and then this is the reflection. And please notice that consistent with what I showed you before, reflection is 100% at the resonance. And of course, this corresponds to the interference that we've been talking about. Now, this, of course, motivated us to consider single atom mirrors. And this is a work which we recently published. And Qiafan Zhao, who is right now my graduate student, and Jiang Liao, I mean, who stayed with me for a very long time, both as a student and a postdoc, but now a professor in China. I mean, they are the main people who really carried out this work. So here we consider, let's say, two atoms forming mirrors, and let's consider just a single pulse, single photon pulse moving in this direction. Then these atoms can now act as mirrors with a reflectivity which we just which I gave you some times ago, would correspond to something like this. Here I draw these curves with the solid curve corresponding to this expression. But of course, if we solve the exact expression, then that would correspond to this dotted line. And what is happening is that basically there are these jumps, and these jumps correspond to this pulse hits this emitter, and then part of it is transmitted, part of it is reflected back, and so on. Here, the x-axis is essentially the group velocity times time divided by L. So this corresponds to essentially the number of rounds that this pulse can make. And it turns out that under certain realistic kind of conditions that we talk about, the amplitude essentially does not go to zero, it remains finite. And here we consider different effects. For example, here we have talked about the coupling strength. G is the coupling strength. If the coupling strength is increased, then of course the results are better. The number of basically rounds can increase, and so on. I mean, here I talk about the effect of this gamma, the decay to the non-propagating modes, and of course, if gamma increases, then worse results would be obtained, and so on. And then we considered now a slightly more complicated system. And here we considered now these two atoms forming the cavity, which I just talked about. And here considering an atom, let's say initially in the excited state. So middle atom is initially in the excited state, and the side atoms, they form the cavity, and we study this problem. This is in a paper which just got accepted, but not yet published. And here we see essentially the same kind of behavior that we would expect for an atom in an excited state confined inside a cavity. What we observe here is basically these damped Rabi oscillations. So this damped Rabi oscillations essentially remind us of the damped oscillations in a regular cavity. When we look at the spectrum of light, which is, let's say, outside the cavity region, in this region and this region, we see some behavior like this. I mean, of course, at the resonant frequency, there's nothing there because all of it is reflected. But we see, as a result of the interference, some peaks here. And this is what reminds us of this single photon, a frequency comb, except for the fact that in this case, we are talking about a single frequency, single photon comb. I mean, it started as a Gaussian, and then it now results in such narrow lines, a single photon frequency comb. I mean, here everything is symmetric. So we have both the left side and the right side correspond to this spectrum. But in this case, we have taken some asymmetric situation for the placement of the atoms, and it gives us, let's say, on the right-hand side, a much better frequency comb than on the left-hand side. Okay, another, I mean, as I mentioned initially, we were interested in studying the effect of a squeezed vacuum. And here we consider the effect of a squeezed vacuum on the atomic inversion. So the idea here is, here we have a system, a 3-level atomic system, and then we have, let's say, some squeezed light, which is incident as a result of these parametric processes from this direction and this direction. And what that means is that essentially all the modes that the atoms see, they are in a squeezed vacuum state. And we recall that Purcell basically showed us that the decay rate can be changed by engineering the vacuum. Now in this case, we have all the one-dimensional modes. They are in squeeze states. I mean, this problem was sort of studied many years ago by Fichek and Drummond. And what they showed was that the maximum population inversion that could be obtained in this system using a squeezed light could be 78%. And what we show is that actually the possibility exists for 100% population inversion. So, okay, so this is a squeezed vacuum, which has been talked about before. You know, I mean, these two modes, squeezed vacuum. I mean, here R happens to be the squeezing parameter, and this M is bounded by this number. In ideal situation, M would be equal to cosine hyperbolic R, sine hyperbolic R. And for simplicity, we take this phase to be equal to 0. And then we write down these equations. I mean, of course, I don't expect anyone to look at them carefully. The only thing that I want to point out is that these populations in level A, B, and C, unlike, for example, for a thermal field, where they will depend only on the populations, rho AA, rho BB, and rho CC. For a squeezed vacuum state, they depend upon these off-diagonal matrix elements, rho AC and rho CB, CA. And I mean, it is the consequence of these terms that we will see a very enhanced population inversion. Here, there are some. I mean, the system is closed, so rho AA plus rho BB plus rho CC is equal to 1. These are just the decays. And here, gamma 1 corresponds to the decay from A to B, and gamma 2 corresponds to the decay from B to C. Okay, so once we write down these equations, we can solve them. These are closed equations. We can solve them for a steady state. And it turns out that when we look at this steady state, it is actually a pure state. Okay? I mean, here we have a state which is pure state. This term A would correspond to the decay from B to C, and the other one. And now from here, what is clear is that if we can have a squeezing parameter large enough that this gamma 1 over gamma 2 it is much larger than this, then we can essentially get population inversion. I mean, this contribution will go to 0, and the population will be obtained here. I mean, that is the case when the decay from here to here essentially is diminished. And under these conditions, we can approach this population inversion 100% under these conditions. How to understand that? So in this case, what happens is that when we apply the field, I mean, these are the terms that really play the role. I mean, these are the terms, I mean, rho AC in some sense plays the role of a level. I mean, we go from C to B, and this is playing the role of a quasi level. There are which provides us a route to go through here to the level A, in addition to going from B to A. And once it reaches here, if this decay rate happens to be very small, then of course the population inversion is obtained. So this is, I mean, another application that we might like to discuss is the deterministic preparation of an arbitrary single excitation quantum state. Since my time is almost up, so let me just give you a physical idea and then close my talk. I mean, so dynamics of a quantum system is governed by the Schrödinger equation. Okay, but what we notice is that if we apply complex conjugate to both sides and replace t by minus t, then we have the same, I mean, the Schrödinger equation, but it is governed by a different Hamiltonian. So this is, here psi 0 through this Hamiltonian gives us psi t. Here psi t through this Hamiltonian can give us psi 0. And what that means is that if we want to obtain a final state, then under this Hamiltonian, then we can start with some initial state which corresponds to here, and then the system evolves under this complex conjugate Hamiltonian and gives the result. So in this case, what we have obtained is that the idea basically is that we can prepare an arbitrary single excitation state for n atoms by doing a reverse calculation, and then shining these pulses onto these atoms basically prepare a desired state for the superposition of this A and B level. This we include in here by just saying that, okay, once the atom is in level A, it can be brought in level C, and then it stays here, and we have a state between B and C, which is in a desired state. So here are, how to prepare a quantum state, an entangled state deterministically. We just need to have a photon spectrum looking something like this, okay? And then very deterministically, we can obtain the desired state with unit fidelity. Okay, so this is all that I had to say. So what I've discussed is that waveguide may be a nice system to study QED effects. It can act as a cavity with atomic mirrors, and it can be a source of single photon frequency comb. It can be arbitrary quantum states can be produced in a waveguide, and population inversion, almost 100% population inversion can also be obtained. Thank you very much.
Thanks, Suhail. So Vitali has a question.
I have a general question. Zuhail, if you take into account recoil of atom in your mirror, this either the atom in the harmonic trap or just free atoms, this will significantly change the result, isn't it?
Well, okay, so we have not included the recoil effects in here. And yes, this is a good question. We have to really study the effect of recoil on some of these effects, yes. But my guess is that may not be so big. For example, this inversion, etc. I think we should be able to obtain to a good level. Yes.
Okay, thank you.
Okay, Olga, you have a question?
Olga,
yes, I have a question. So, Zuhail, is it possible somehow to understand, intuitively, why the comb is formed in the transmitted line, and what does determine the width of the peak in this comb?
Okay. So basically, this effect comes about because of the interference.
It's clear that it's interference, yes, but somehow.
A way to understand it, I think, would be that if I have, let's say, multiple atoms, the periodicity is what creates the band gap. So this comb we can look upon as some kind of an optical band gap. The basic physics in here is that because of the periodicity of the atoms, we will get an optical band gap, and that will be manifested as a frequency comb. This is I think this is a good explanation for the effect.
Thank you.
Okay, well, I guess we are getting quite late, so let's thank Suhail again.
Gert has a question, I think.
Well, okay.
Gert has a question.
If we can afford the time, yes, Gert?
Yes.
Yeah, no, only quickly, Zuhail. Thank you very much. We are actually doing something very similar in 3D with a deep parabolic mirror. I will look at some of your papers, so we also consider this time reversal symmetry. So the atom, when it evolves unitarily from excited state, it will be exponential. It will be exponential decay. So you must and a Lorentzian profile in 1D. This is the same, right? You also have exponential decay and Lorentzian.
Yes. I mean, the thing is that of course this our results they did not include or considered the decay in the non-propagating modes to be small, but of course this decay was included completely. Yes, I mean basically you have to do a calculation to come up with the photon pulse that will be needed for the state preparation.
Yeah, we avoid this by doing everything in 3D, but maybe you can discuss this offline. Thank you.
Okay. Thank you very much.
Okay, thanks, Suhail. So our last speaker is Denis Seletsky from Polytechnic Montreal, and he's going to talk on non-classical pulses for sub-cycle quantum optics.
Thank you very much for the introduction. I'm assuming that you can hear me and see my laser pointer on my slide. If you don't, okay, perfect. Okay, so yes, I'm faculty at Polytechnique Montreal, and I recently started my sabbatical in the Max Planck Institute for the Science of Light in a group of Maria Chekhova. So I know we're severely kind of out of time here, so let me just very quickly introduce what I want to discuss. I want to give you a little personal motivation for the work that I'm presenting. And then because I always run into these, let's say, misunderstandings of frequency versus time, I want to spend a little bit of time on that, followed by the introduction, how field result detection works, and finally, on our main topic of the presentation, which is quantum field result detection. Okay, so quantum states of light, I guess this is all very familiar to you. If we think of classical electrodynamics, obviously in the phasor representation is just a well-defined arrow that's rotating at an angular frequency omega. Of course, this violates Heisenberg uncertainty principle, so we must introduce this uncertain disk, which of course is nothing more than vacuum mode. And a coherent state then in this picture is just a displaced vacuum that's, again, rotates with this angular frequency. And we know how to quantize this system. This is, I will skip that. And manifestation of vacuum fluctuations, I guess also for this audience, are very clear. You have atomic physics, spontaneous emission, Lamb shift. In nanoscience, Casimir effect gives rise, is risen out of the change in density of states of vacuum in and out of the cavity, but also there are interesting manifestations in even cosmology on microscopic scales. But anyway, I'll skip that in the interest of time. So what I want to focus on is, okay, we have this Hamiltonian, we're climbing the ladder. Okay, so if we start with the first mode, so these are all eigenmodes, so they're obviously time independent by the nature of this eigensolution. So, but this is essentially a time-independent mode, which we call it vacuum state. So it evolves as a function of phase, or this angular frequency, and hence as a function of time. Now, if we go to the next mode, it's our single photon Fock state, and we can keep climbing to 2 and so forth. And you can see that the distribution of electric field, instantaneous distribution of electric field, if we could measure that, would look something like this, time independent, again, because these are eigenstates. Now, if we have some kind of a superposition of these eigenstates, for instance, a very, specifically prepared one, so-called coherent state, then we'll see, obviously, time evolution. So the question that I want to ask is, can we actually use a technique that measures, that samples this time evolution of the field, okay? And probably some of you are already thinking, yes, we are doing that in quantum optics. I want to maybe challenge that a little bit. All right, so let's think, how do we measure quantum state in a traditional way? Well, we take our input state, in this case, let's say coherent state, and we combine it, we beat it with a local oscillator. Okay, so it's a version of the input state that's classical, so very bright coherent state. It's phase locked, and then we can impart two different frequencies: the cosine one, the in phase, and the quadrature one. Right? And then we analyze both of these signals. One gives us projection on the horizontal axis of our phasor diagram. Another one gives us projection on the vertical, and hence we can reconstruct the Wigner function of the state. Okay, so let's kind of put it in a slightly different way. So let's imagine that we have this quantum state that we're analyzing. This is an unknown state we want to analyze. And let me represent it in the frequency domain as some kind of a distribution function in frequency, E sub q. Now, what homodyne detection is doing, as we just discussed, this local oscillator, we introduce some kind of a mode, which we call local oscillator mode. It has finite support in a frequency domain. And then it's clear that the signal that we detect in this homodyne detection is nothing more than a product of these two amplitudes evaluated at the position of the spectral support of the local oscillator, in this case, omega naught. Okay, so essentially we select omega naught, that is our local oscillator mode, then we do our projection, and then we measure. If we want to reconstruct all of these, well, I guess we probably should have some way of sliding omega naught or doing something else. So my point that I want to convey here is that omega local oscillator is it's within the spectral support of the unknown quantum state that we want to measure. That's that's given. And it's given by the fact that we are doing linear interaction. We essentially need a region in frequency where two modes are indistinguishable. If they are, then we have interference, right? So we have essentially, in this technique, it's already clear that we must have well-defined frequency for the local oscillator. And what that means, if you think about it, if you have localized in frequency, that means you're delocalized in time. So information that you measure in this homodyne detection, I'm arguing, is cycle averaged information, okay? And to me, this is information, this is a picture of a photon, okay? So we have well-defined frequency. This is kind of a traditional language of what we would use in quantum optics. So now let's take this picture, this is frequency domain, and let's now port it into the time domain. Okay, so we have some kind of a distribution of a quantum state evolving in time. Instead of taking a localized object, which we call local oscillator in frequency, now let's take a localized object, let me also call it local oscillator, but now in the time domain. So it's clear that now we have a special time tau naught as opposed to special frequency omega naught. Now the signal also comes about where the two overlap, that's clear. But now keep in mind, this signal is in the time domain. So the product in the time domain means it's a convolution in the frequency domain. It's clear that this interaction is nonlinear. And this is the point. So whenever you have a linear interaction, like in homodyne detection, you're in the frequency domain. The moment you impose nonlinear interaction, you're local in the time domain, and hence this is a natural basis, let's say a conjugate basis to the homodyne detection. So you can see that if we have our local oscillator very localized, shorter than half cycle of the oscillation of this quantum field, then when we were to measure in such a process, we would pick up a local amplitude of the quantum field, local amplitude frozen in time. And you can see that because of this, the information in this measurement scheme only has access to the amplitude of the field, and hence all the frequency information is lost. So one way to call it is subcycle detection. Another way to call it is local field detection. We have no information on the frequency of that field. We have only information on the amplitude of the field. And as opposed to quantum optics, where we have kind of actors of our story, our photons, Here, I would argue that we really have access to quantum electrodynamics, where the actor of our story is now a field as opposed to a photon. Okay, if you don't like quantum electrodynamics, I'll call it subcycle quantum optics. So this is my way of kind of motivating going from extreme frequency to extreme time domain picture. So now let's think about what do we actually need for this. So we have our quantum field that's oscillating in time. We need our local oscillator that's shorter than half a cycle. Well, what technology do we have access to? Well, we have kind of nice fiber lasers that give us pulse durations on order of 6 femtoseconds. So that's good. That gives us a natural time scale on which we can think about. And then if we want to impose the condition that the half cycle should be longer, then it pushes our, let's say, support of our quantum field to be laying in the terahertz and the mid-infrared frequency range. All right, so we have, let's say this, we have 6 femtosecond pulse that's technologically given. I have a reference here, and we're now selecting this mid-infrared frequency range. What about nonlinear process? We need the nonlinear mixing. All right, so this is done by so-called transverse Pockels effect. You've seen Gerrit Loick's presentation just a few presentations ago, where he talked about DC Kerr effect. Remember, if you apply a DC bias to a nonlinear crystal, it induces polarization rotation. Well, this was a Chi3 version, or 4-wave mixing version, and this is a 3-wave mixing analog of a DC Kerr effect, and we can call it Pockels effect. So the idea is the following: if you apply a DC bias to the crystal, then when light of certain, our short wave packet propagates through this crystal with a slightly broken symmetry due to the bias, then polarization state of that pulse will change. So this is a Pockels effect. Now imagine now the situation that instead of applying a DC bias, the bias is applied by the excursions of the quantum field itself. And because of our condition that the local oscillator is shorter than half a cycle, in that reference frame, you can think of it essentially as a DC bias on the crystal. All right. So if you want, I can summarize it in the following way. If we have a no impinging field on the crystal, then we have polarization state of the local oscillator. After the crystal will be the same after the quarter wave plate. So we're doing polarization analysis. After the quarter wave plate, then it's circular, then we do projection back to horizontal vertical, we get 0. Now if we introduce this mid-infrared field, it breaks the symmetry, that changes the polarization state. We get either positive or negative signal depending on the directionality of the terahertz field. So this is clear that at the given temporal overlap of the local oscillator and this terahertz and mid-infrared field, we have information on the instantaneous amplitude of that mid-infrared field. And now by simply scanning the delay of one with respect to other, we can reconstruct the total wave function. All right, so just to show you that kind of this works classically, so just to kind of give you an idea how this works, if you think of it as essentially as an oscilloscope for light, right? So you have this electro-optic crystal, what we just discussed, it comes from the ellipsometry. We can convert it to the actual electric field, which you want to think of it as it's electric component of the electromagnetic wave here bunched at the terahertz or mid-infrared frequencies. And here you can see the output of that measurement. So essentially it's indeed a wave packet that's oscillating, at a characteristic frequency here, an order of 10 femtoseconds or so. And here it shows the duration of our local oscillator. Now, because we have amplitude information, we can now take Fourier transform and actually get both amplitude and phase. And this is interesting in its own right, but this is classical, right? So now let's think about what do we need to do for the quantum measurement. So for the quantum measurement, we essentially need to look at the statistics of our measurement. And moreover, let's just take our classical measurement and let's suppress the classical amplitude. Let's not put any classical amplitude onto the crystal. then classically we would expect to measure 0, but of course quantum mechanically, due to the ever impinging vacuum state on the electro-optic crystal, we expect to measure some kind of polarization noise of our probe. And it turns out that polarization noise, we can go into the discussion during Q&A, depends sensitively on this 4 space-time volume of the probe. That means it depends on the duration of the probe and the spatial extent in the transverse direction of the probe. So anyway, here we are showing that for a very short duration of the probe, something that will pick up a lot of, coupled to a lot of vacuum fluctuations, you see that the histogram of the measurements is centered at 0, as you would expect. Classically, we are measuring nothing. But then with respect to the longer probe, we see that there is a broadening of the distribution. And that broadening is consistent with the amplitude of the vacuum. And this was the result that we obtained back in 2015. Not only stretching it in time, we can also stretch it in space. And again, we get very nice agreement with the theory. And we have this scaling of, again, coupling to the vacuum amplitude for ever decreasing size of the probe. Now, you can see that these signals essentially look like Gaussian or derivatives of Gaussian. And for obviously, since vacuum state is essentially a Gaussian state, it's well characterized only by the second moment, by the variance of this distribution, we have no problem. But my question that I want to ask is, how about analysis of non-Gaussian states? For instance, if we have a cat state or some other more interesting state than a vacuum state, can we think about analysis? And it turns out, I'm skipping the details, but this technique, because it relies on classical, essentially, coherent state probe, and coherent state is another Gaussian probe, you can see that there is a, in some sense, mismatch in the statistics. So it's what thinking about what it takes to probe non-Gaussian states of light in the time domain forced us to think about quantum enhanced electro-optic sampling, and this is what I want to present in the remaining few minutes that I have. So okay, so this is our electro-optic sampling. We have our quantum state of light, we have our localized local oscillator, and we have this electro-optic crystal and ellipsometry. This is exactly what we've discussed so far. Now let's think of modifying the scheme slightly. Let's think of a strong pump that pumps parametric down conversion. It generates daughter states. One of the daughter states is sent to the crystal, and we're doing exactly the same procedures as what we already discussed. And another daughter state is sent in a post-selection detector. So spontaneous parametric down conversion, obviously, I don't have to tell you, is a very nice way of producing, let's say, correlated entangled single photons. Turns out if you pump it very strong, you can generate very bright squeeze states of light. So Maria Chekhov is one of the world experts here at Max Planck on this topic. And more importantly for us, these two twin beams will have correlations, if you analyze them in a proper way, that will go will be correlated beyond their Scheit noise value. So now, if we want to apply this scheme, I haven't told you what is our post-selection protocol. If I have time, I will. But more importantly, this is maybe a little bit more of a nuanced topic, because now we're trying to analyze states in the time domain. You have to understand that our parametric down converter has to emit single temporal mode. So let's discuss what we mean by that. So essentially, parametric down conversion, if you think of it, interaction of a short pump with the vacuum, there is obviously phase matching condition, which determines the coherence, temporal coherence of that nonlinear process. So in some sense, if you want to think about it this way, it's essentially a nonlinear beam splitter. Pump light introduces some kind of nonlinear coupling to various modes of the vacuum. It can be the single mode, first mode, so forth. And then these modes get amplified and come out in the signal and idler beams. So if we want to think about the number of temporal modes, what do we mean by temporal modes? Essentially these functions, right? So this is the first temporal mode, second temporal mode, and so forth. So the number of temporal modes will be nothing more than duration of our pump pulse scaled, normalized by the coherence time of our parametric down conversion. So essentially one of the coherence, one over the phase matching function. So if we want to have very nice sub-cycle resolution with our pulses, we impose that we need to have very short coherence length, but still short enough to give us nice amplitude in the parametric down conversion. And obviously our pump has to also match that short coherence time. So in terms of classical pump, obviously we first need to have a very short classical pump, very energetic classical pump. So I'll skip the details, but we have a non-collinear optical parametric amplifier that Patrick Cousson, who is the PhD student on the project, has built. And this delivers over microjoule of pulse energies at sub 10 femtoseconds. And we have a decent repetition rate, which means we can collect statistics fairly efficiently. All right, so then if we go to the next step, so now we have this strong classical pump, and it generates our entangled twin states. So some details on the crystal. So obviously, as I said, we want very high gain to have a large number, a photon number in our entangled states, and from that we use very thick crystal. Unfortunately, with short pulses and very thick materials, there is group velocity dispersion. That's a common problem. So we have this trick that we operate at the zero dispersion wavelength. So we select our pump pulse such that the parametric down conversion occurs at this degeneracy point. So anyway, I'm here showing, I know that I have just 1 minute left, so I'll skip through some details. Tell you that these are spectra of individual pulses. And you see if there were multi-mode, you would see a lot of different oscillations. But here, just spectral decomposition shows that you have 80%, more than 80% in the fundamental mode, and quite a few percent in the higher order modes. I can also tell you that we analyze statistics of each of these independently. You can see beautiful linear dependence on a logarithmic scale, which means these are essentially single mode, confirming our single mode, our modal analysis. And you can also see, if you look at the variance of the photon number difference between signal and idler, it's suppressed quite a bit, showing you excellent correlations. We are not at the shot noise or beyond shot noise yet due to technical reasons, but we are approaching it within a factor of a few already. And maybe just lastly, I want to say that imagine these are entangled pulses. These are highly correlated pulses. And they're also very energetic. They contain 10 to the 6, 10 to the 7 photons on average. In fact, this intensity is enough to generate second harmonic these pulses can generate their own second harmonic, and we can use that to analyze the pulse duration. So we can tell you that our parametric down conversion is measured 14 femtoseconds in duration and Fourier limit of 10 femtoseconds. So I'll skip the post-selection protocol. You can read about it in this physical review letter if you're interested. But just to say that this post-selection protocol allows us to do a sub-cycle detection of quantum fields, also coupling to the higher order statistical moments, meaning this more sensitive to the non-Gaussian states of light. So I guess with that, I'll just thank my group members, my collaborators, and thank you for your attention.
Well, thanks very much, Dennis. So Gerd has a question there.
Yeah, thank you for the talk. Very interesting. I had a question. So I think I understand the electro-optic sampling, but coming back to initially when you talk about this asymmetry between heterodyning or homodyning in the having a local oscillator in the frequency domain and in the time domain, you say in one case you are in the linear regime and the other case you are in the nonlinear regime. In principle, you could also in the time domain, I think, be in the linear regime if you had a detector that could sample the electric field with this high time resolution, but this you don't have. So this why you have to look at in the frequency domain again, and this is why you have nonlinearity, not from principle, but from, so to say, from practicality, right?
Well, I would say if we had detectors that could follow the oscillation of light, we would not need homodyne detection. Also, we would just measure directly the voltage oscillating on the oscilloscope. So we don't have that, obviously, so it's a moot point. But yes, if we were to have it, then that would be true.
But local oscillator also amplifies the signal. So if you could follow it, but it's too small, you still would. So then you wouldn't need the resolution, but for the amplification, it would still be nice. Yeah. So I think this actually, I followed some of the papers. So the way you talked about it clarified some things for me. So thank you very much.
I'm glad. Thank you very much.
Well, since no one has a question, can I ask a question?
Of course.
Yeah. So in the first part of the talk, you were saying that you would detect an electric field in the terahertz domain, but then when you went to non-Gaussian states, would you still use the fields in the terahertz domain, or you would use the fields in optical domain?
Well, so yes, for us to satisfy this subcycle condition, the pulse duration has to be shorter than half a cycle of this quantum field under study. So because we are, 6 to 10 femtoseconds on the duration of the local oscillator naturally pushes us into the mid-infrared. And this is good for two reasons. Even though I mentioned terahertz intrinsically is not so good. Why? Because of the black body radiation. Up to about 25 or 30 terahertz, the occupancy per mode is actually not limited by the vacuum. It's limited by the black body radiation. So if you were to be measuring at those low frequencies, you'd be just measuring thermal fluctuations. But the way our pulses, that's the reason why our pulses are so short. They actually couple into frequencies that are 60, 70, 100 terahertz. And in those ranges, thermal fluctuations are exponentially suppressed, and the dominant contribution is the vacuum fluctuations at those higher frequencies. And that's mid-infrared.
Okay, so you would use the SPDC to produce the photons at mid-infrared, right?
We can have various ways of producing photons in the mid-infrared. SPDC can be one of them. It can be just optical rectification. There are a number of ways. The concentration of this work was more on producing correlated states, one of which would be doing the electro-optic measurement, and another one would be using as a post-selection witness.
No, I thought in the last part of the talk, you were trying to detect non-classical states using the same techniques that you used earlier. And so for non-classical state, you use SPDC.
Right. So non-classical. So we have, in some sense, two non-classical states. We have non-classical state 1, which is doing the sampling, and we also need to prepare the mid-infrared quantum state that we want to analyze. So I haven't yet talked about how to do that.
Okay. Well, thanks, Dennis, and let's thank all these
maybe
speakers.
one short question. So, but if you would use, for example, attosecond pulses, then would you move to optical domain, right?
Yes, of course. So this is, I think we are just trying to stimulate your theoretician brains to think about this new approach to, let's say, subcycle quantum optics. And of course, theoretically speaking, you can dream about it. Experimentally, we're not there yet, but we are getting pretty close. One is for several reasons. One is the repetition rate needs to be very high in order for us to do proper quantum statistics. Mm-hmm. And B, lasers operating at the attosecond, they're not yet shot noise limited. But again, technology development is moving extremely rapidly. So I'm expecting in the next decade, we'll be able to talk about sampling of quantum fields in the visible.
Okay, thanks, Dennis. And let's thank all the speakers in this session. And good night, everyone.
Thank you to Girish. Thank you.
Yeah, my pleasure.
Good night. Bye-bye.
See you tomorrow. Bye.
Bye.